So I should say we have a really a great panel that comes at these questions from many different directions. So so let me introduce the panelists as they are pinned up. So we have Nathan Wiebe, who is he's from the University of Toronto, and he's worked on many aspects of quantum algorithms for the electronic structure problem, for quantum simulation, Hamiltonian simulation, scientific computing. So there's James Whitfield, who is one of the pioneers in quantum algorithms for electronic structure, starting with his work in his PhD with Alan Asper-Guzik. Lin is my colleague from the math department at UC Berkeley, and he has worked extensively on classical electronic structure simulations with this numerical analysis lens, but in the last few years he's gotten increasingly interested in the quantum simulation aspects of this problem. And Birgitta Whaley, who's again my colleague in chemistry at UC Berkeley. Birgitta has been working in quantum computing for a very long time. We co-direct the Berkeley Quantum Information and Computing Center. She's worked extensively on quantum error correction, decoherence-free subspaces, quantum control. She sits in the chemistry department. She's been thinking a lot about both near-term quantum algorithms for quantum chemistry, as well as more scalable algorithms. So let's start with. It would be good to hear from the panelists about their reactions to Garnett's talk. Let me just say before you start. Let me just say, speaking as a computer scientist, first I really appreciated from Garnett's talk, from your talk, that it provided a really accessible window into the methods, some of how a chemist would look at these problems. I'd like to sort of throw out a couple of sort of issues or questions that I'd like to see if it can be addressed in this panel. So one of them has to do with the fact that, well, of course, ground states are, computer scientists know and love because, it corresponds to the kinds of questions we ask in complexity theory. But when one's talking about chemistries, are excited states also of interest? And if so, is there a nice formulation? So for ground states, there's a very nice formulation for us to think about as computer scientists, which are the interesting ones, so it sort of says, okay, these are the interesting questions. What's their complexity? But if they are really hard to find, then presumably even real systems don't find them, if they are computationally intractable. And so how do you think about this? And is there some nice model so that we can start thinking about them? And then the second question I had was of a similar flavor with respect to not just the statics, but dynamics. And so there we have this whole notion of Hamiltonian simulation. But again, my understanding, and I think this is what maybe Steve Flamier was referring to, is that, well, in practice, you're only interested in smaller parts of the puzzle, and the resources required to simulate the entire system in full detail would probably be too much. So again, is there a way that we can simplify and think about these problems from, stepping back from a computer science viewpoint? But okay, so with those, I'd love to go to the panelists and hear your perspective and about the talk.
I assume I'm going to let the others talk, and I will I talked enough, yeah. But I mean, at the end, if I can give some opinions.
Okay, great.
Yeah.
Okay. Somebody.
So okay, unless somebody else wants to go first, I can start. But all right, cool. So again, thanks a lot, Garnet. Obviously, my the point of view is diametrically opposed to yours when it comes to this. But one thing I do want to say is that, despite the fact that I disagree with many of the fundamental conclusions that are being made here, one thing that I think is vitally important for everybody to get from this is the fact that there are many examples in chemistry that are vastly easier than what you would end up believing from just taking a look at doing naive FCI in order to be able to solve the particular problem. So, I think that's a vital point. And also, I think, when looking at benchmark examples of highly correlated quantum systems, making sure that you're setting everything up to avoid, kind of like the danger zone of having one-dimensional molecules that DMRG might be really awesome at and things like that. But I guess, the part that I think that I differ with Garnet's interpretations. I think I agree with all the numerics. He always does a bang up job with all of that stuff. It's undoubtedly 100% correct from my point of view. But one of the dangers that I think ends up coming up with this actually goes back to an older result from adiabatic quantum computing. And so there was this early result that was put out that by one of the founders of adiabatic QC that ended up claiming that basically 3-SAT or K-SAT more broadly can be solved in polynomial time on quantum computers by using the adiabatic algorithm. And basically what had happened is just the examples that we're taking a look at weren't drawn from a set that would end up approaching a phase transition where the typical problems ended up going from easy to hard. And this, I think, ends up raising a big and sort of deeper problem that ends up coming up when both computer scientists and chemists talk about both of these things. One of the things that Garnet is amazing at, I think, is like what Umesh said, is that Garnet's one of the few people who can kind of talk in the middle of these two camps. But one of the big challenges that ends up coming up is that you can't really formally get the asymptotic scaling, of course, from small numerical examples. You never know whether or not you've actually hit one of these transitions to go into the hard instances. And on top of that, you're not ever really sure whether or not the examples that you've taken for the benchmark set that you take a look at are representative of what the problem is as a whole. And finally, I guess one of the things that I think we, in order to turn this into, I think, more of a constructive discussion about what the scalability of the electronic structure problem actually is, really having both sides agree upon what the formal definition of the problem is going to be. Is it in terms of constant accuracy? Is accuracy a variable that we can change? How can the initial how can the nuclear configurations be contrived for it? These sorts of problems really these things have to be addressed before I think we can actually get to a full conclusion about it. But again, going back to the initial thing, I think that that's a vital point. The other thing that I kind of really want to make sure that people recognize is that, well, I'm not sure I buy Garnet's arguments about the accuracy of state preparation. This is probably the biggest, even for people who believe in the exponential advantage hypothesis for electronic structure. The question about the overlap for state preparation is totally unknown from a rigorous perspective. And that's something that as a community, we need to think more clearly about no matter what. But yeah, so that's kind of like my initial thoughts about this.
I'm not going to respond in detail because I feel that I can talk later. But I just want to say, Nathan, I appreciate those comments, and I think they're very reasonable comments. I don't disagree with them, although I draw different conclusions.
Exactly. Yeah.
Well, since Nathan poses the kind of like idea of the paper, I don't know the perspective of James and Birgitta on this. So I feel that as a co-author of the paper, I should say something along a different line just to balance it out. So yeah, I mean, as a co-author, I indeed agree with Garnet on at least most of the points. But while Nathan said that Garnet come from the quantum chemistry community and can really talk to like both the quantum chemistry and the theoretical computer science, I guess I'm also like in the middle, but in a different sense, in the sense that I'm in the middle of nowhere. But there's some actually some advantage by being in the middle of nowhere, so I can at least see my perspective of both communities. So I think one of the outcome of this research that done by a lot of this numerics, very carefully carried out by Garnet's group, is that it undoubtedly raises the question, as Nathan said earlier, how we should actually think about this kind of initial state preparation problem. Or when you actually do some resource estimate, is that really reasonable to really assume the overlap is equal to 1, and then we do some quantum phase estimation, and that's it, right? I mean, there are some papers are along this flavor. I can come back to resource estimation a bit later. But from my perspective, the classical heuristics, there are numerous of those. I mean, it's very, very hard to pin down the asymptotic complexity of even much simpler quantum algorithms, not to mention much simpler classical algorithms, not to mention the very complex ones, let's say, density matrix embedding theory. But on the quantum side, at least based on the tools we have right now, the situation is actually somewhat simpler. There's this VQE part, which is hard to analyze analytically and theoretically, but it's going to be invaluable for initial state preparation, right? Because generically preparing a good initial state is hard. But once you have sort of like a good initial state, then you don't have that many options really. There's a QPE and there's a post-QPE. And they differ in terms of some scaling with respect to precision, with respect to the initial overlap, but the basic idea are actually the same. It's basically some sort of filter and filter out the unwanted things and leave the things you have, and and make sure you analyze the errors, things don't blow up. There's not much pollution, so on and so forth, and then you're done. So the mechanism is not that complicated. And there have been a lot of progresses in the past few years on this, and hopefully there's something from our group will come out tonight and along this line, and especially targeting the early fault tolerance setting. But I would say that all the mechanisms, they're similar, they're understandable-ish, and there's some performance guarantee. Then there's this big question, which is how do you really go to the initial overlap? Like that is, let's say you don't need to go to initial overlap equal to 1, but the initial overlap that's omega 1, let's say 0.01. Then there, roughly speaking, there are 2 approaches one can do. One is to just do harder, work harder on the heuristics, could be VQE, could be some other things. And so Garnet showed that sometimes, or adiabatic state preparation is not good enough to just work like with a pencil and paper. Sometimes it's really insightful to just carry out some of the simulations. I think some more work along this line should be done for hard chemistry problems. Requires a lot of talking of the 2 communities. But there's another one that was raised earlier, which is also very timely and very, very important, which is generically all the QPE, post-QPE algorithms, they will fail if the initial overlap is bad. I think Nathan gave an example of flipping the coins, see the chat. And indeed, that's, the difficulty of this thing. But maybe, at least for some initial state or for some quantum algorithms, they can work somehow in some regimes when the gamma is actually small, the overlap is small. That's possible, and that's vastly understudied in the literature. I think that's really a timely and important question. That's what I think.
I think I'll follow up on that. I think I'm really looking forward to reading the paper. I think this was a fantastic talk. A lot of things that I thought, and I think it's really nice to see numerics behind it. This idea of QMA versus BQP is really, I think, at the heart of the story. And you said at the end of the last slide that this is not about excited states. I think excited states exactly we get to BQP. And I've had a feeling for a long time as the VQE literature started to expand that these are all trying to solve a QMA hard problem, that there may be no actual way to do so in the instances that are hard for both quantum and hard classically. And I think Garnett's, at least what he's shown, goes to show some evidence to that argument. And so I thought that was really impressive. I also think that it's one of the things you outlined inside of your talk that I thought was quite interesting, and it was very much a passing moment where you mentioned that going from a model system to the ab initio system doesn't change the complexity much. But I think there's an aspect of that that you can also read as these are the things we know how to do. We've learned how to do them by going through the toy model, figuring out what's not important, what we can throw away, what approximations to make to get to the ab initio model with the right techniques, the right methods. And I think that's really what's driven a large part of what quantum chemistry has become and what it can do. It's just on the fact of what we're trying to do. And it's almost like machine learning in the sense that it's trained to do this. And so I think having quantum computers go after the things that quantum chemistry is trained to do is not a formula for success. And I think this is where I really think that you've kind of laid out arguments to that point. I also think there's one other thing to point out what Nathan said about pinning down the question of quantum chemistry. I think when I hear computer scientists approach this idea of quantum chemistry, there's often these arguments about scaling and how the system goes as you go to very large system sizes. But when we think of quantum chemistry, quite often we don't go to large system sizes, and it's not really a sensible thing to talk of a super large, biomolecule. You wouldn't use electronic structure to approach that. You start dealing with thermodynamics, vibrations, and other things entering. That I think that there's some limit to what the scaling even makes sense to talk about for an electronic structure problem before you start talking about something entirely different. And so I think how does it actually play with the theory of complexity is something that I think is kind of very much open to see how that actually plays out. I would be interested to hear a little bit about how, in the beginning, you talked about this L being the parameter you're talking of scaling. And quite often when you go to translation invariant systems, it's the scaling with the number of K points that really determines the complexity. And so thinking about how that might actually interact with some of these arguments, whether it's just the same argument or whether it changes because you haven't changed the number of atoms and just changed the number of K points that you need to integrate over. So yeah, like I said, I'm looking forward to reading the paper and hearing what everyone else has to say.
Hi, I should say something now. So Garnet, great talk. Thanks very much. It's very stimulating and also a very, very complete sort of summary of the state of play right now, I think, with regard to the ground states. So one comment which I think really pulled, for me, for my own interest, I pulled out of your presentation was the statement that you've made that, well, we want to put in more structure to get good initial states. But if we do that, the danger is that we might be making better ansatz states for the quantum calculations, we might be shooting ourselves in the foot in terms of advantage because we're finding out how to make better heuristics also for the classical method. But I think this is actually a place where effort should be focused basically on taking as much structure as possible from classical quantum chemistry to the quantum algorithms, but still to identify the places where classical techniques still cannot solve these. And so the way I'm looking at electronic structure these days is more, I know you're focused on ground states, but I'm looking at it more in terms of ground and excited states together, looking at methods that can solve for both, and in particular focusing on strong correlation problems. And I noticed you didn't really say much about multi-reference states or even multi-determinantal states, which seems like a natural thing to use for better ansatzes just to start with right now, even from a given reference. But when you're looking at strong correlation systems without doing tensor networks and so on, but in practice, so one often uses multi-reference Hartree-Fock states where you have states which are non-orthogonal. And if you start dealing with non-orthogonal methods, you can clearly identify places where in principle, there's an exponential advantage. Because if you start to make overlaps with coupled cluster techniques with non-orthogonal reference states, then you can't actually truncate very easily. And in principle, the coupled cluster expansion continues forever, and then you do have an exponential problem. And that's a problem. So we're actually looking at that right now. We have we're writing a paper on it coming out soon, probably, hopefully soon. But it does seem that that's a problem where, at least on paper, there is something which is, I'm not sure how generic it is, but when you're dealing with these ground states and low-lying excited states together of these metal complexes and so on as a generic problem, I think there is room there for other techniques distinct from the method that you mentioned on the classical side, which would be interesting to do, but can only be done in a very approximate way right now. But we would scale exponentially, even for small systems. They would scale exponentially in the basis size. So that's one thing. And then also, yeah, so I was also going to put in a plea for, I think excited states are just as important as ground states in terms of chemical reactions. All the photoactivated reactions in biological systems all proceed on excited state surfaces.
After all, there's just more of them.
There's more of them, yeah. So I think it's good to stimulate algorithms, not just for the ground state. And as James says, maybe there is more of an advantage there. But even also, then also I'd like to make a comment about the accuracy. So quantum chemists really like to nail this accuracy of the energy, the ground state energy, to within this 1.6 millihartry chemical accuracy. But sometimes you have a system that's so complicated that you aren't so much interested in knowing, say, the sequence of states, the ground state and the first few excited states. Your first question isn't necessarily exactly what energy they are, but it might be, what's the ordering of the spin states? What is the spin? If you have high spin complexes and they, like the oxygen evolving complex, the manganese atoms in the oxygen evolving complex, that's a very complex spin chain of reactions, electronic reactions going through different spin oxidation states, or oxidation states of the manganese corresponding to different spin states. And there you were really interested in knowing the ordering, first of all, before you want to actually nail down the energies. So I think there's maybe other targets that one could go for.
Interestingly, that's actually kind of a decision problem, like the kind that Ike was talking about.
Actually, it is, yeah. It's multiple, yeah. It's not a binary decision problem, but it could be formulated as a decision problem. That's a good connection. Yeah. So maybe, Garnet, I would be interested to hear if you could say something about your perspective on excited states and whether you think the same kind of conclusions about EQA would hold as well, or whether it's a completely different ballgame in the excited states.
Sure. I mean, okay, so I mean, many points have been raised, and so I don't think, and let's see. So I'm trying to think. Maybe there's some generic comment I can make that addresses a lot of points, which is that, and then then I try and address the excited state question very specifically. But the generic comment is, and this relates to what maybe Nathan's original points. So Nathan in the beginning asked the question in some sense, how do I know that if I don't look a bit more carefully or look more deeply, and this is also related to Sergio's point, you'll see something else. Currently we may not be in the asymptotic regime. I may not have looked at quite the right problems. These problems might have been centered, and those are all fair points because one's doing a finite amount of calculations and finite amount of data. But they're very important because asymptotics can be very different, right? It's a bit like the Riemann hypothesis. It doesn't matter if you compute lots of zeros. It's not really, you don't really know the answer to the question. But I would just say that evidence, this hypothesis is, the point of view I'm proposing is actually very easy to disprove, because if you can find evidence on the other side, that's sufficient.
There's QMA hard results that we have out right
Oh,
now.
no, yeah, but I've sort of excluded, well, okay. I mean, there's, actually, I don't know what you're referring to. I mean,
Well, what I'm talking about is like the generalized electronic structure problem, right?
Yeah.
I'm not talking about any particular molecule. If we knew a particular molecule, that would be fantastic.
Yeah.
But the formal problem that encompasses what we talk about when we talk about quantum chemistry has QMA hard instances.
Right.
And so then what that ends up
construct an explicit abstract construction, right?
I mean,
circuit.
Be careful about the QMA constructions for electronic structure. You really don't have that much information inside electronic structure Hamiltonian to actually manipulate. You only have the scalar potential. So it's not actually that easy to say that they're QMA hard.
But formally, one can write a circuit to, Hamiltonian construction, right, for the QMA. So one can construct it. But okay, so all I'm saying is it would be very good if one takes the very skeptical view of the conclusions of my talk. I mean, one can be skeptical about any aspect, but of the kind of conclusions, then I think the most productive thing is to construct some evidence on that, numerical evidence for the other, then one would change one's mind.
But numerical evidence won't settle the skeptics. We need theoretical evidence. So how do we go forward and actually develop? Because we've got theoretical evidence on the hardness side. It's just a question of extrapolating out to the cases you studied numerically. How can we kind of, get theoretical evidence that we can, extrapolate out and maybe say that these cases that we suspect to be hard are in some sense isolated or not typical of the ensemble that we really actually care about in the chemistry case? And I don't know how to do that.
So also let me mention another point, because there's a common misconception, like when people have listened to my talk and then try and sort of like compress in their head to one point, that in the end, my talk is just about saying something related to the fact that ground state is formally in QMA. But actually, that's really not the way that's actually really not what the talk's about. The talk is really about, actually, perhaps most of chemistry is not in QMA. Right. Actually, I'm excluding from the very beginning the kind of problems that are in QMA. But then for those instances, perhaps they also happen to be, classically easy, right? So it's really talking about the easier type problems rather than the really hard problems. And that set is very hard to characterize. That's the theoretical problem.
Yeah. And this is the big challenge, right? Is that I don't know how to characterize what we mean by typical molecules.
So I think it's interesting. There's two things there, right? So I think, Nathan, your question is about typical. And I think Garnett's talking not so much about typical, at least what I understood is talking about what conditions make it easy to solve electronic structure. And, is that satisfied or not? So it's asking about the characterization that makes it not QMA hard anymore, then you can make some solutions, some progress towards that. And I think that's a really interesting question about ground states, because it's really when do heuristics work? You could ask a lot of questions about heuristics, but at the end of the day, I mean, if you take the generic ground state problem, then it's QMA hard. If you take some very, very restricted one, then perhaps, as Garnett's pointing out, maybe if it's easy to solve classically, or if it's easy to solve quantum mechanically, it's easy to solve classically.
And it's hard to find the bit that's like easy quantumly and hard classically, right?
Another thing,
some evidence for that would be.
That's also really important to take a look at is that, if we take a look at, say, standard NP complete problems, like, for example, MaxSat. If you take a look at that, there's different approximation ratios within which very naive and efficient classical algorithms will be capable of producing the solution within desired accuracy. And so the question, I guess, about chemistry, right, is that, is there something equivalent that maybe these results are stumbling on, that the formal problem is actually hard. It's just we don't know what the kind of approximation ratio is before we start the accuracy is so high that the typical instances are hard.
So if I have to interject here, so just from a pure, complexity viewpoint, as you said, okay, so there are the QMA hard problems, for which even quantum won't solve them. Then you say there are the problems that you can currently say, well, maybe these couple of quantum heuristics would solve, and maybe you're saying, well, I don't see any examples where classical algorithms wouldn't solve them. But then you can approach the problem from a different viewpoint, and you can say, look, there are still a number of quantum, chemistry problems, electronic structure problems that you don't know how to solve classically, but nature knows how to solve them, because it's obviously finding that electronic structure, whether it be a ground state or maybe not getting to a ground state, but something else. And so in principle, we think that should be, if you simulate the dynamics, you should be able to get to that structure. So now we could sort of say, well, there are similar problems classically, for instance, protein folding, etc., where we said, look, it can be done, therefore it can be, since nature solves it, there must be a way to do it on a computer. And in fact, AlphaFold sort of does it, right? It's one of the big successes of deep maths. Mm-hmm. So one could sort of say, well, look, why shouldn't there be a classical algorithm then, if nature does it? And of course, it could be the case that when nature does it, it's going through some states which are enormously entangled, and we won't even have any reasonable answers to represent those intermediate states. And that might be a reason why there should be a quantum algorithm, but not a classical algorithm for finding these. So how would you think about, so this is of course naively thinking as a computer scientist, but what would you say to that?
I believe, Umesh, I think you're addressing me, is that correct?
No, yes, please. Yes. Yeah.
Okay, so I would just say, I think the first part of what you're saying is asking about the relevance of QMA, because QMA is not so relevant in the physical, in some sense, because if something finds some state, it presumably found it in a reasonable amount of time, right? It's executing dynamics that is BQP, not sort of QMA. I think that's the first.
Yeah, maybe what I was saying was, no, I was sort of acknowledging your point that the QMA complete problems are not going to be the place where you find quantum advantage, because even quantum algorithms are going to have trouble with them.
Yeah.
So yes.
Yeah. So the question is then what to do with the remaining set, and so I think the real Achilles heel of rigorous quantum algorithms is the fact that locality is so prevalent in the low energy states, right? And so I think for quantum algorithms to have an advantage, you do need to rely on these states which have some really global entanglement structure, and as the system size gets bigger, you retain this global entanglement structure more and more, it just keeps going out. And then at least from daily experience in the kind of bread and butter type of chemistry that molecules that one thinks about, there tends to be, our experience is that things have after some point behave independently of some other point of some other region. And that sort of kind of is, that is so common that it makes it a little bit hard for me personally to see why one should always have some dependence on some global information out to infinite scale. There's just some scale after which a table is a table separate from the chair, So, but of course it could be some scale that's really large, and for all intents and purposes, the locality doesn't manifest fast enough that it saves you computationally, and but yeah, I think that's why it's not that easy to find exponential quantum advantage. Now, in the case of dynamics, and so Birgitta, just very quickly, you asked about excited states and what I think about it. I think many statements about ground states, the low-lying excited states are not so different. That's my view, but very highly excited states can be very different. And so I'd say that I don't think the first excited state necessarily, I don't think there should be another paper in the first excited state, writing a paper in the ground state. But I don't think it's going to be significantly different when you go to the first excited state in practice. But highly excited states, though, can be computationally very different.
Well, what about, let me bring up conical intersections. What about, so the really tough problems where you have to then have intersection of potential surfaces and breakdown of Born-Oppenheimer approximation.
There are many problems that are very difficult and are they're currently intractable because there are too many degrees of freedom and so on. So, yeah, I mean, I suspect that at least at low energies, you still don't have the sort of polynomial exponential kind of divide, isn't changed too much at low energies, whereas you have to perhaps go to high energies to like chaotic type things where you get this really sort of exponential stuff reappearing.
There aren't really any good classical methods for dealing with dynamics of conical intersections.
I agree. Yeah, I mean, anything coupling electron nuclei quantumly, I mean,
Right.
we currently don't have good methods, and perhaps it will never be practical. But it might. I guess my point is it may be a polynomial problem rather than even it can still be very impractical as a polynomial.
Can I ask one question? I think in a large part of the arguments both you and Lynn kind of set out with was about adiabatic state preparation more broadly. So is it possible that to get a quantum speed up or to even get exponential quantum advantage, you might need to avoid preparing a state, to just take a random state and somehow use information about the Hamiltonian or something?
Well, I mean, very, very roughly, I mean, saying you can, you might be able to, do something locally, right? And then, then in that sense, bypass a global overlap. And like if you had completely isolated systems, you determine the ground state by determining the ground state of one at a time, right? So, that type of heuristic is probably, could be imagined, but maybe Lynn had a different perspective.
No, I actually agree that very much in line with what I said earlier, that this kind of theoretical studies of different strategies that can somehow let you bypass this constraint by the global overlap would be very valuable and seems to be underexplored. And I also want to say something from my personal perspective, which is, again, from the perspective in the middle of nowhere, that, I mean, a lot of the discussions so far about the power of theoretical studies. And if you really dive a little bit deeper, you find that it is specific about the power of complexity theory, theoretical studies. To me, to a person like me, while I appreciate that there have been numerous developments in complexity theories that address very challenging problems, I somehow always feel that complexity theory is just too big of a gun, or it's like a too coarse-grained to really analyze some of the effects we just mentioned earlier. That's the conical intersection. It's like using a tweezer with diameter was like 10 meters to pick up a ball or something like that. I mean, it's possible, but it's just feel awkward. Many of these systems, iron sulfur clusters or right, and nitrogenized things, they're quite specific, and the effects are pretty delicate. To me, while theoretical studies, they are very useful, but what may be equally useful, or maybe let's say equally useful, is a more careful resource estimate. And if there is a quantum computer one can run it, I'll be thrilled just to run it there. But before that, we do our best to take into account both the best heuristics and just estimate the cost, right, in a reasonable way, and to balance out the cost of the initial state preparation and the post-initial state preparation steps. It's not like the initial state preparation has to prepare a state with a fidelity 1. That just sounds, yeah, that's too hard, too high a task for heuristics. And then marry this cost with that of the best classical algorithm, because as Garnet said, there's this numerator divided by denominator problem. We can maybe do some theory on the numerator side, which is the quantum. The denominator is just nasty. Nobody in the classical world even worry about these problems, right? So this will never be settled if nobody is working on those the complexity of those classical heuristics. I think the best way should be heuristic versus heuristics. So that's it. Maybe I'm too pessimistic in terms of the power of theory. There definitely have been a lot of progresses in the past few years, but I really think in the end it should be heuristics versus heuristics.
I guess the real challenge is that we don't have a fault-tolerant quantum computer. And because we don't have that, we can't really test the quantum heuristics at the scales that we would like. in order to, because ideally, once we have that, right, then the ultimate point of comparison will be dollars to solution.
And I'll just say, I've heard that argument before, Nathan, many times, and it's to some extent true, and I'm waiting for my friends to build me a quantum computer. So big. But I do think that people can test them much more than they currently do.
I just want to second Garnet's point. Like, for example, many of the studies here, right? And you do some n/2, n/4 type of simulations. Why you can do that? Well, that's the best you can do with the DMRG techniques, but it doesn't mean that you learn nothing from those calculations. I definitely agree that you can do more and try best to have a more concrete numbers versus numbers instead of complexity versus complexity. That doesn't address the problem of conical intersection.
Well, I think one other thing that would be really interesting to add, just to follow up on Lynn's point, is that we think about the theoretical methods of computer science. Quite often it's a worst case scenario. And I think getting at what Nathan's asking, how do we know that this doesn't work, or how do we know about chemistry? Can we get an actual ensemble upon which to do average case complexity, to actually talk about, maybe statistical properties of an average molecule? Nathan had a paper many years ago where they tried parameterizing some ensemble of molecules that I think it might
very poorly.
Yeah, well, at least it's an idea, but that I think it's worth going back to see, can we characterize things theoretically better by having something to average over? And I think this might be an interesting way to kind of address Lynn's point about things being too heavy-handed inside of complexity.
I think, but one thing, though, that is definitely a good way that I think we should be using complexity is that, we should be really skeptical of any result that ends up contradicting well-motivated complexity theoretic conjectures. Like if we ever see anything that suggests, P is equal to QMA, specifically, that's a big red flag. That is, if true, we should all go out and share the $1 million prize for this, because I'm down to split it evenly if you guys are. But the thing is that we should use that aspect of it. But of course, we should also, I agree completely with the other side, right? Just because of the fact that, there exist worst case scenarios that are computationally suspected to be difficult, that doesn't mean either that the typical ones are computationally difficult. And it also doesn't mean that your particular problem, whether typical or not, is computationally difficult. So I think, developing better ensembles is a great way of going about it. If we want both sides to meet in the middle. The second thing is getting a firm agreement upon what the computational problem exactly is, and asking, okay, well, are we giving ourselves access to the ground state? Are we not giving ourselves access to the ground state? How, being able to pose something that's a well-defined problem that both sides agree on. And then I think the next point that really is needed in order to get an understanding about this is to really actually kind of, I think, nail down, we really want to nail down, once we have those things, what the computational phase diagram kind of ends up looking like. As we decrease epsilon, my strongly held belief is that as we shrink our error tolerance smaller and smaller and smaller, that will hit a regime where we'll see the computational overhead blow up for many of the methods that are efficient at fixed precision. And I'd like to get an idea, once we've got an agreement upon, what the problem is, how that ends up looking like. And then if we can give some numerical evidence about that, then I think that might be helpful. But better yet, asking, are there simplified versions, perhaps, that aren't electronic structure, that maybe are a little bit easier, that we could actually get more a concrete understanding about, and have some rigorous theoretical scaling arguments on the other side. And maybe we can somehow sandwich the problem of how hard real chemistry is in between the extreme examples on either side.
Okay, great. Well, Nathan, you may well have the last word here. So let's see, Garnet, that was a really fantastic, very clear and very thought-provoking talk. And Birgitta, James, Lynn, and Nathan, that was really, really good insights into these issues, and also to the audience for fantastic questions in the beginning. So next week we have a colloquium by Mark Zandri on verifiable quantum advantage without structure. So so look forward to seeing you then. Thanks a lot.
Thank you, everyone.
Thanks, Garnet.
Thanks. Bye.
Bye.
Okay.
Everyone.